Let's go ahead and get started. Hey, it's back. All right. Okay, listen up, please. All right. So, as far as the test is concerned, I've gotten several questions about the test. I'm not a machine, people. All right. I'll grade them as soon as I can, and hopefully that will be over this weekend. Okay. Yeah, I'm not that fast. But this one will go pretty quick because all it is kind of right or wrong on all of them, so it should be easy. Listen up. So what we're doing now is we're kind of transitioning. The whole last unit was about what?
Ionic bonding.
Good, ionic bonding, okay? I'm glad that you're able to tell me that. It makes me feel a little bit good. So this is on ionic bonding, or this last unit was on ionic bonding. Now we're moving into the other one, covalent bonding, okay? We kind of skipped, the other major section was metallic bonding, okay? And metallic bonding, we kind of skipped over that one, which is unfortunate because it's interesting, but we just don't really have time for it, and there's not a whole lot to it. And by not a whole lot to it, I mean there's a whole lot to it. But we're just not going to cover it, all right? So we're going to talk about covalent compounds. What we're learning today, I think you're going to find it much easier than what we were doing with naming and writing formulas for ionic compounds. What's that? Good. Some of the other stuff we get into with covalent gets a little bit tricky, okay? So we'll get there when we get there. But for today, you guys should be fine. I don't think you're going to have any issues at all. Some very common compounds are covalent, okay? In fact, pretty much your entire body is made up of covalent compounds, all right? So they are very, very important compounds. So important that if you decided you wanted to go into the medical field in any way, you would probably end up taking a couple of semesters of organic chemistry in college. And organic chemistry is basically just carbon. It's everything that carbon can do, okay? And not even everything, because carbon can do some inorganic things too. So, anyway, carbon-based compounds are all pretty much covalent. And the reason for that, if you look at where carbon is on the periodic table, where is it? It's right in the middle, right? Okay, so remember talking about that group in the middle is a little weird because it could gain 4 or lose 4, so it doesn't usually do either of those because that's a lot of electrons to lose or gain. What carbon would prefer to do is, rather than lose or gain, what would it prefer to do? What covalent compounds do? You're going to have to think back to 8th grade for this one.
Oh.
Yeah, so, okay, so let's see if we can get this. If ionic compounds, there's a transfer of electrons. The electrons are moving from one thing to another. Then what might we be doing in covalent? Cooperation? Covalent? We are sharing electrons, right? We're cooperating, okay? So that's what's happening. It's not like one atom is taking electrons from another. In covalent, there's a sharing of electrons. Now, they're not always shared equally, okay? We'll get to that later. But they're sharing the electrons in between them, and that's their strategy, okay? So that's covalent compounds. Covalent compounds are going to be formed from 2 or more non-metals. Now, hear me when I say this. With covalent compounds, we are talking about the blue elements on my periodic table, okay? And how they combine with one another. With ionic, we've been talking about how the tan combines with the blue metal and a non-metal to make an ionic compound, all right? With covalent, it's all blue and sometimes green, all right? Because hydrogen is involved with those covalent compounds a lot. Does that make sense? And every once in a while, you do get a yellow with covalent compounds. The reason they're metalloids is because they can form ionic or covalent compounds just depending on the situation, okay? But we're mainly talking about the blue. All right, so notice CO2, that's carbon and oxygen. They're both blue, right? Ozone, O3, that's oxygen only, and that's blue. CH4, Remember I said the hydrogen is involved in these sometimes. Okay, so you've got a blue and a green, CH4. And then BCl3. Now boron's one of the yellow ones, okay, which can sometimes act like a metal, sometimes like a non-metal. And then you've got chlorine, which is a blue, all right? So those are the things basically on the right side of the periodic table are the things that are going to combine here to form covalent compounds. And like I just said, ionic compounds are metal and non-metal, okay? So that's one really easy way to tell whether something is an ionic compound or a covalent compound, is just looking at the formula. Is it a metal and a non-metal, or is it two non-metals? What if it has a polyatomic ion? What kind of compound is it going to be then? I'll give you a hint. Polyatomic ion. Ionic compound, right? Okay, does that make sense? So if it has a polyatomic ion, it's going to be ionic, okay? If it's two nonmetals or maybe a metalloid and a nonmetal, then we're talking covalent. That's how you tell the difference. Okay, so naming these things is, at first glance, it's a little bit trickier than ionic, all right? Because if I've got something like oxygen, and what we've been thinking is oxygen forms what charge when it forms a compound? 2-, right? Because it needs to gain 2 electrons. So, but what if an oxygen combines with another oxygen? Don't they both want to gain 2 electrons? That doesn't work out very well. One of them's not going to give up their electrons to the other one, right? So if I can't work this out based on charge, like I can with the ionic compounds, because with an ionic compound I can say, okay, lithium is going to form a 1+ charge, bromine is going to form a 1-, so this is a 1-to-1 ratio, LiBr. And if I call this lithium bromide, because of where they are on the periodic table, I can figure out what the formula for that is going to be, right? If I tell you lithium bromide, you say, okay, lithium's a 1+, bromine's a 1-. They combine in a 1-to-1 ratio. That's LiBr, okay? You can figure that out. But when I tell you a covalent compound like carbon and oxygen, if I told you to try and figure out how carbon and oxygen combine with one another to form a compound, well, there's a couple problems here. First of all, you can't really use their charges to figure this out, right? Because then you're going to get something weird like, oh, well, maybe carbon would be a 4+, oxygen's a 2-. Okay, bad example because actually, by some freak of nature, works. So don't forget that, okay? Never tried that before. It didn't work. It actually worked. That's why it didn't work. So anyway, if you're trying to figure something out like, well, carbon monoxide, right? CO. That's a compound. That's a compound that will kill you. All right, so don't breathe that in. Carbon monoxide. Okay. Carbon monoxide can be produced by incomplete combustion. What that means is if your fuel burned perfectly efficiently, the way that it was supposed to, if you had the perfect fuel-to-air ratio all the time, when you turned on your car, it would be only carbon dioxide, CO2, coming out of your exhaust. Now, even CO2, if it fills up a garage, will suffocate you. Okay, because you need oxygen in order to live, right? But CO, carbon monoxide, is actually poisonous on top of the whole suffocation thing. So that's worse. It doesn't have to be as concentrated for you to die from the carbon monoxide. And that happens because there's never a perfect fuel-to-air ratio in a car engine. So a car engine's always going to produce some things that it shouldn't be producing, like carbon monoxide, nitrogen monoxide, nitrogen dioxide, some combinations of nitrogen and oxygen that end up polluting the atmosphere, okay? So that's one of the problems with car exhaust, and there are things inside a car that try to help limit the pollutants that come out of the tailpipe, like the catalytic converter, if any of you are familiar with cars. But that's the purpose of the catalytic converter, is to take out some of those pollutants as it goes through the exhaust before it comes out your tailpipe, okay? Anyway, point is, carbon monoxide, CO, if I looked at the charges on these two things, it wouldn't make sense that they combine in a 1-to-1 ratio, would it? Okay, because this is either a 4+ or a 4-, and this is a 2-. So you can't do that with covalent compounds, all right? The other problem is, there are different ways that these things can combine, like the example I just gave you. If I tell you carbon combines with oxygen, well, it could be CO, carbon monoxide, or CO2, carbon dioxide. both of these are compounds that exist in nature, okay? There is no such thing as LiBr2. Because lithium's a 1 plus charge, bromine's a 1 minus, so they always combine in a 1-to-1 ratio, right? But you can have CO or CO2. So how do you name something like this? I can't just call this carbon oxide, can I? So what did I do with those two compounds? And you probably didn't even notice me doing it. I put a prefix on it, didn't I? Carbon monoxide, carbon dioxide. See how that works? Okay? So here's why this is kind of easy, actually. The prefixes tell you the number of atoms in the compound. So you don't have to do any charge crossing or anything like that with covalent compounds. All you have to do is look at the prefix in the name. Okay? So you're going to like this. Once you learn the prefixes, which I don't think is going to be too hard for you.
So this works with anything? Like,
This works with any, no. This works only with covalent compounds. All right? With ionic compounds, you don't use prefixes. You name it the way that we learned last chapter. Okay? But with the covalent compounds, if you've got two blue things combining with one another, or maybe a yellow and a blue, you're going to use prefixes. All right? Just some special rules here. You don't have to put mono on the first element. Right? Notice when I said carbon monoxide, I didn't say monocarbon monoxide. Okay? That would sound weird. So you don't have to put mono on the first element if there's only one of it. Okay? But on the second element, you do have to say mono. I don't know why that's the way that it is, but that's the way that it is. Okay? And then the same thing that you did with ionic compounds, you change the ending of the second element to IDE. Okay? Carbon monoxide, right? It's not carbon monoxygen. It's carbon monoxide. Okay? So you laugh because it sounds funny because you're so used to carbon monoxide. You sort of understood these naming rules without realizing that you understand them. Here are the prefixes, okay? I don't think very many of these are going to give you trouble. There's maybe a couple, all right? Especially if you've had a math class where you've had to learn probably most of these, okay? So mono is 1, di is 2. That one might give you a little trouble because bi can also mean 2, right? But just remember in chemistry it's di. But think of carbon dioxide, and that's going to help you, all right? Tri is 3, tetra is 4, penta is 5, hexa is 6, hepta is 7, octa is 8, nana is 9, deca is 10. I'm guessing nana might be the one that would give you a little bit of trouble because we're not used to that one. But the rest of these you're pretty familiar with already, aren't you? Yeah. Yes, sir. Oh, sorry, I should be following along on the notes. Where are you looking on the notes? On 1B. 2.
Blank nitrogen, blank oxide.
Oh, where it says practice? Okay. I just don't think we've gotten to that yet. You know what? These examples I don't think are on your notes.
yeah, they are. They're down to
Yeah, they're different examples. So I'm showing you these, and then, so don't worry about writing anything on your notes now. We will get to the practice that's on here, okay? All right, so everybody okay with the prefixes? That make sense? You do need to know those, all right? So one thing that you should probably memorize, but honestly, again, memorize nana and you probably got it, okay? Yes? What's that? On 1B, yeah, and there were 4 elements, or 4 examples, weren't there? So here's your examples. You can choose any 3 of these 4 to put in the blanks on 1B. Okay, it just says examples of a covalent compound. Ozone, carbon dioxide, methane, boron, trichloride. And you can just write down the formula. You don't need to write down obviously there's not enough room for the name in those blanks. Okay? So pick your 3 favorite and put them in the blanks. Oh, or if you can't, choose between them because they're all so great, then you can put down all 4, right? Yeah. You know what? Methane actually doesn't smell.
They put it
It's other things in the methane. Yeah, they add a smell to the methane so that you can smell it so that you don't, die.
They do. There's something else in your house. They add a smell to.
Maybe natural gas.
Yeah.
Yeah. Yep. Which is propane.
Propane, what's your mind?
Or am I thinking I'm going to have to look into that. Maybe I'm wrong about the methane. Maybe the methane does have a natural smell. It's the propane that they have to add the smell
Yeah.
to.
It's natural gas.
Yeah, I don't know. Yeah, I'll look at that.
Monoxide, you cannot smell that.
No, carbon monoxide you cannot smell. Which makes it even more dangerous, right?
I know a guy that my dad works with.
Oh, wow.
Like, you know that house.
Yeah, that's horrible. And the people on the video will never know what's horrible, and I'm not going to repeat it. Okay. So as far as examples here, let's just work on this. Now, someone said that they hadn't seen the prefix tetra before, for 4. Maybe something that'll help you with that one. There's this old game that old people used to play called Tetris, okay? You guys ever heard of Tetris before? Yes? All right. So Tetris, basically, if you think about Tetris, they were all of these shapes were made out of squares, right? Okay? 4-sided squares. Okay? So I don't know if that'll help you or not, but yeah, Tetris, Tetra, 4. All right, so CCl4, how would we name that? Just based on the rules that we just learned. Okay, wait. Monocarbon, right? No? Oh, you don't put mono in front of the first one. Okay, I forgot. Thank you. I didn't forget. I was just pretending. Okay, so carbon, and then what? Tetra, chlorine? Chloride. Okay. Put the IDE ending at the end. There it is. Carbon tetrachloride. That's another one that you probably don't want to ingest or inhale in any way. You know, a lot of these covalent compounds are that way. Not all of them, but especially the non-polar ones, which means nothing to you yet, but it will. All right. N2O. Wait. I thought you didn't need a prefix in front of the first one. Oh, okay. If it's more than one, you need a prefix in front of it. So
Wait, what do you mean it's more than one?
Well, there's 2 nitrogens there, right? The subscript tells me how many of each element I have. Okay?
Dinitrogen.
So dinitride? Oh, okay, so no ID ending on the first one? Dinitrogen, that sounds weird, doesn't it? Monoxide, very good. You have to put the... Now, here's another just kind of... I'm not going to ding you on this on the test, okay? Sometimes you drop a vowel, right? Notice, we didn't say monoxide. That's just awkward, right? Monoxide, okay? So sometimes you're going to have trouble figuring out how that prefix fits with the rest of the element, especially when the element starts with a vowel. Just, make it sound as natural as you can. I'm not going to count off on a test if you do that, if you do it incorrectly, all right? SF6. Sulfur. Hexa. Fluoride. Sulfur hexafluoride. Do you feel smart just saying these? You should. No? Okay. I do. I don't know. All right. So this is pretty easy, right? Okay. You don't have to worry about charges. You don't have to worry about Roman numerals. You don't have to worry about polyatomic ions. The only thing you have to worry about is prefixes. Okay? Yeah. So that's why we try to separate these, because it gets harder when you put them together. And I may give you an assignment at some point where they're all together and you have to figure out how to name ionic versus covalent. Oops. Guess they were all written there. All right. So here's the ones you... What's that? So here's the ones that you have on your notes. Was that a tiger? That was weird. Okay. Anyway, these are the ones that you actually do have on your notes, all right? So some of this has already been done. You just need to fill in the extra part. So this first one, carbon monoxide, all right? So hopefully that's Should be fairly easy. Second one, carbon dioxide. Third one, phosphorus trichloride. 3 is tri. Fourth one, we already did that one. Carbon tetrachloride. Oh yeah, we did that one too. Dinitrogen monoxide. And now we have 3 more with no blanks, so you just have to do the whole thing, okay? So what about P2O5? How would we name that? Okay, diphosphorus, not diphosphide. Don't put an IDE ending on that first word, okay? Diphosphorus. I like that. Pentoxide, okay? You can say pentaoxide. I think technically it's pentoxide because you dropped that vowel. Yep. Whoops. Yeah, usually. Unless it makes it sound... you just kind of go with how it makes it sound, honestly. Okay, so that one again, diphosphorus pentoxide. And you will not get counted off for pentaoxide. Okay, what about the next one down, Cl2O7? Dichlorine heptoxide. Again, heptoxide is fine. Yeah. Yeah, it's just awkward if a lot of times you have those 2 vowels right next to one another. And then the last one. Okay. I'm good with that for now. All right. Well, yeah, we're going to talk about diatomic elements later, I hope. Are we going to talk about diatomic elements later? Is it in there? Okay. Okay. Yeah, we're going to have to probably add that in. You know what? Yeah, I'm not, we don't have anything else to do today. So, okay, let's talk about the diatomic elements. We're pretty much done with the naming. See how easy that is? That's your quiz, well, Monday. Yeah, I don't expect you to be here tomorrow. Because, you know.
Oh, it's Saturday.
Yeah, it's Saturday tomorrow.
Today feels like a Monday. No.
That's because you've been gone.
No, yesterday felt like a Friday.
Okay, I need a periodic table.
I know.
I know there's one on here somewhere. Uh-oh. Did it lock up on me?
I was never correct. I was correct.
Ah. Okay. You know what? I'll just open one from here. What is happening? Okay, let me get to a periodic table and then I'll show you something here. 4. Just going to be sideways. Awesome. All right. So, you guys have a periodic table on your notes. Listen up. Maybe the best thing to do, though, would be to have out your personal periodic table, and we can talk about this if you look at your personal periodic table. Not necessarily, as long as you're looking at this one. Okay? All right, or that one. Not necessarily, no. Okay, so here's the deal. Listen up. This is important, and I'm sorry it's not in the notes. You might jot it down on the side of your notes somewhere, just so that you have this. And it will be on this video, so you can always go back and look at it, okay? Diatomic molecules. You ready?
Yeah.
Diatomic molecules. There are certain elements on the periodic table, they're just super insecure, all right? You ever had a friend who just could not ever, ever be by themselves? Ever. And if that happened, maybe you are that person, right? If that happens, you just like start shaking. You get nervous, right? Okay? I have to be around people, okay? There are certain elements on the periodic table that are like that, all right? There are actually 7 that will never be by themselves if they can at all help it. And if they are by themselves, they start destroying things, okay? So it's bad if these elements are by themselves. You don't want that to happen, okay? So here are the elements These are the elements that are diatomic. They are never by themselves on the periodic table, okay? You ready? Well, here, let me get back to the screen. Okay, nitrogen, oxygen, fluorine.
They are always by themselves?
No, never by themselves. Chlorine, bromine, iodine. Oh, and hydrogen.
Wait, so nitrogen, oxygen.
I got them all circled right now.
What's
Fluorine. Fluorine. It's kind of weird. Oxygen in nature is never by itself. Or like I said, if it is, it's causing some serious trouble. Ozone, well, here's the thing with ozone. The reason that it messes with you so much is because a lot of times that ozone will break down, and then you've got two oxygens that are fine. You got one oxygen that's all by itself, and it's like, what's going on? And then it starts, like I said, destroying things like your tissue. Okay? So ozone up in the upper atmosphere, good, because the sunlight comes in and the ozone absorbs that UV light, okay, as it breaks down. Ozone down here where we can breathe it, really bad, all right? So we don't want ozone down here. We want it up there, okay? So a lot of times those high pollution warnings that you get, it's because of high levels of ozone in the lower atmosphere, okay? Yes. Okay, so everybody listen to this. You ready? These are the ones that cannot be by themselves. So what that means is, the reason we call them diatomic, let's say that you have a pure sample of nitrogen. That's all that there is just nitrogen. The nitrogen atoms don't want to be by themselves, so they pair up. Okay? So what you end up with, and this is going to go away again, what you end up with here for nitrogen, the nitrogen we breathe in, the air around us, 78% nitrogen. Did you guys know that? 78% nitrogen is in two. All right? It's not just nitrogen. It's not just one or individual nitrogen atoms you're breathing. It's nitrogen atoms that are paired up to form a molecule. They're always in two. One nitrogen covalently bonded to another nitrogen. All right? It's always O2. It's always F2. It's always Cl2, Br2, and I2, and H2. Yeah, see, I didn't put these in the order that I wanted to.
Oh,
well, I've got a couple of ways for you to remember this. All right? So let me rewrite it. So my students came up with this a couple years ago, and I liked it. And it works in this class. Okay, so there's your list. I2, Br2, Cl2, F2, O2, N2, H2. If you need a way to remember which ones are diatomic, here's your sentence. I broke clean forks over Nick's head. Sorry, Nick. Okay? I broke clean forks over Nick's head.
wait, what are those called?
Diatomic molecules. Here, I'll write that down too. Diatomic.
So I broke clean forks.
I broke clean forks over Nick's head. Well, it helps if they're clean. Yeah, sure. I mean, it doesn't specify they're metal forks, right? So it could be plastic. Yeah, it's a very good mnemonic, all right? They took a long time to figure that out, like a minute. I broke clean forks over Nick's head. That's one way you can remember it. Now, another way, if you're just looking at a periodic table, you remember how I told you there are 7 of them? Well, look what I kind of did here. That sort of looks like a 7, doesn't it? Wow. And guess which one it starts with on the periodic table? Nitrogen's number 7. Whoa. This is weird, right? Okay. So start with nitrogen. Yeah, and hydrogen you just have to remember, right? So there are 7 of them. 6 of them make a 7, starting with element number 7. And then you just got to remember hydrogen's in there also, right? Yeah. Yeah, you got to go backwards, basically, okay? I broke clean forks over Nick's head, okay? So there's no reason you shouldn't remember that, all right? Those are your 7 atoms on the periodic table that always pair up, all right? They are never going to exist by themselves in nature in normal circumstances.
So would you say it's chloride or would you say chlorine?
Okay, so when you are talking about naming these, then all I want you to say is iodine molecule or bromine molecule. You don't have to put the IDE ending on these. Okay. Now, if you do say that, if you say if you said diiodide or dibromide, I guess I'm okay with that. I mean, that's not the way we normally name them. Okay.
Would you rather us for dichloride to say?
For Cl2 down here, just chlorine molecule is fine. Okay. Probably that's the best way to say it. If you said dichloride, like I said, I don't think I'm going to count off there because you're following the rules for covalent compounds, right? Where you could get yourself into trouble, though, later in the year, is if you forget that these are the diatomics, okay? And we might come back and hit this again when we talk about writing chemical reactions, but it doesn't hurt to cover it here since we've got the example. Yep. Yeah, that would always work. Yep. Yes, ma'am.
So do we need to remember all the prefixes for the test, or are we going to get?
So what you need to know for the test, the diatomics I just taught you, you probably need to know those for the test, and the prefixes you're going to need to know. I'm not going to give you the prefixes, all right? Honestly, that will take you 5 minutes to memorize, and then you've got it, okay? That's not hard at all. So that's not like memorizing the list of polyatomic ions. There's no way that you could do that, right? Well, you could, because I did, but you have to like see it a lot over and over and over and over again. So the polyatomics I wasn't worried about, but the prefixes you guys can get, okay? All right, so last 15 minutes or so, I'm just going to give you guys a worksheet where you can practice naming and writing formulas. You guys should do fine on this, and then we'll have a quiz probably first thing on Monday, all right? Signing off.